It's going to be lecture number 21, optimization. Optimization. Okay. It's like chapter 4.4, I think. All right. So we'll begin with a loosey-goosey definition for optimization. Okay. Let f of x be a function modeling some scenario in terms of x, right? To maximize f of x, take f prime x, find critical values, and ah, and okay, you know, in terms of x, and I be some interval to maximize f of x over the interval I, find all critical values of f of x over I, and determine the absolute max in I to minimize f of x over I. Find, it's the same as here basically, right? Find all critical values of f of x over I. So make sure you're not out of bounds. And determine the absolute min in I. Easy peasy. We'll make a little note. If I includes one or both endpoints, check the output of f of x at the endpoints, just in case. Okay. So for example, right, let's say our interval I is equal to open A to closed C, right? Let's say A lives here, C lives here, open A looks like that, close C looks like that, and then let's say that f of x is going to be a function in orange. It's going to go something like that, right? And then off to infinity it goes, or whatever, right? Obviously, this right here is going to be open, not a problem. This is going to be one of the local mins. This is another local min. This is a local max, right? However, this is inclusive, and this is higher than this. You see? Which means this is the absolute or global max over the interval I. Okay, so check your endpoints if they are included. What I'm actually going to do instead of what I did in my in-person lectures, I'm going to throw all of my definitions first and then do some problems. Okay. Another definition is going to be your profit, revenue, and cost function, okay? Let X be some quantity of some product. Then first you have R of X is the revenue in terms of X. So this is telling you how much money you make at any given quantity X in your interval. It might have like a restricted domain or whatever, so just be mindful of that. 2, C of X is the cost total. These are both total, by the way. To produce X number of product. And 3. Ready? If you have your revenue, your income, and you have your cost, which is, I guess, outcome, right? Let's just cut that out. That's cheesy as hell. If you have your income and you have the cost, right? You can find your profit by saying profit is equal to revenue minus cost. That's it. This is your profit function. This will cover like overhead and stuff like that. All right, easy money. Big picture, right? Let's note P of X equals 0 when R of X, your revenue, is equal to your cost. That's where you break even. Ooh. Okay. I'll throw one more definition at you. These definitions are literally only so you can do the worksheet. They're not that serious. Okay. Um, marginal revenue and cost. Marginal is equal to the revenue prime, the derivative of the revenue. Your book calls it M of R or MR of X, and I think that's silly. Your marginal cost is equal to C prime of X. And again, your book calls it MC of X. Okay. All these tell you is rate of change of revenue, which is how much money your next product will make. Right, like typically speaking, right, if you have like a linear function, like you're selling like, I don't know, apples, let's say X, for like $3, right? Then the cost or your revenue for apples will always be $3, and then like let's call it like R, right? And then your cost is 1x because you bought each apple for $1. Then like R prime is equal to 3 and C prime is equal to 1. And that's not too interesting, right? Um, but not all revenue and cost functions are linear. Most products actually get cheaper the more you make, and you actually make more money the more you sell. So just something to note. Um, and then you also know to maximize profit, you want p prime of x, right? But here's the trick, right? You know p of x is equal to r of x minus c of x, right? Which means you know that p prime of x is equal to r prime x minus c prime x, right? Just a sum and difference rule. But to maximize this, you want, or minimize, I guess you can minimize profit too. P prime x is equal to 0, but that just gives you r prime x minus c prime x equals 0, which gives you r prime x is equal to c prime x. If you had a hard time following this, please revisit your algebra. Um, but anyway, I think that's kind of cool. So let's do some problems. This is synced with worksheet 21. And I will be doing problems 1 through 4 on this video. Okay? It'll be fine. And I'll show you guys how I typically like to organize my work too, okay? So problem number 1 says, find two positive numbers whose product is 120 and minimize the sum. Okay, two numbers. Let's call them A and B, such that this is what I advise to my in-person students as well, okay? This is where my equations are going to go, my initial equations given to us by the problem. Well, what does it say? It says, 1, you want the product to be 120. A times B is equal to 120. And 2, you know that you want to minimize the sum. So the sum of A and B, I like to write as a two-variable equation, is equal to A plus B. We'll note that we want to minimize. Okay? The next step is turn everything into a single variable equation. Single variable equation. You want to use the equation you're optimizing, okay? So we know that S of A comma B is equal to A plus B. That's a two-variable situation. We don't want that. What we do know is A times B is equal to 120. So A times B is equal to 120, which means I know that A is equal to 120 over B, right? This goes back to your linear algebra, or not your linear algebra, I'm so sorry, your algebra 1 intuition, okay? So S of, since we're subbing out A, we know this is an equation in terms of B. It's going to equal, what does A equal? A equals this, 120 over B plus B. Okay, we now have our single variable equation. Next, we're going to optimize it. I'll do that in blue. Actually, let's do in purple. No, let's do an orange. Yeah. So you know that S of B, again, S as a function of B is equal to 120 over B plus B. I don't love this. I'm going to write this as 120 B to the negative 1 plus B, right? And to derive that, I'll write it in a slightly different shade of green. S prime B is going to be just a quick little quotient. No, not a quotient rule, a quick little power rule, okay? Negative 1 times 120 times B to the negative 2 plus 1. you don't know how I got this, please review your derivatives. Okay? And I'm actually going to write this as negative 120 over b squared plus 1. If you struggled with this step, review your algebra. Okay? Then you're going to optimize. Let's do this in yellow. So you're going to find your critical values first. You know that S prime B is equal to 0, which means negative 120 over b squared plus 1 is equal to 0, which means 1 is equal to negative 120 over b squared, which means you have b squared is equal to, oh, sorry, not negative 120, positive 120. 120, and b is equal to positive and negative root 120, which is equal to positive negative 2 root 30. If you're struggling with this step, review your algebra. Okay? Okay, easy money so far. Now you're going to want to verify. I'm low-key kind of running out of colors. Let's use, yeah, low-key kind of running out of colors. It's okay. Yellow, orange, different shade of pink. So verify. Using your sign chart, right? Okay. Now, remember, you want two positive numbers. If it helps, you can always write that down here. A and B are positive, right? Any constraints, I'd write it in that little bubble. Okay. So you know that in your verification step, you're kind of blocked out at 0, right? And that's going to be open circle. That is to say, you cannot use 0. You have to use everything to the right of it. Okay? Okay. Negative 2 root 30 is on the left side of 0. Negative 2 root 30 out of bounds. So we do not have to look at this. Okay? And then we'll mark positive 2 root 30. Okay? Now, to be very specific, for critical values, right, you also have b equals 0 because your function's undefined there, right? S prime is undefined at b equals 0, but mins occur where S prime is defined. So although b prime at b equals 0 is a critical value, we don't want it. That and the fact that it's out of bounds, right? Like we want strictly positive, 0 is not positive. Okay. Anyway, so you're going to pick a number between 0 and 2 root 30. I'm going to choose 1. Okay. So S prime of 1 is going to equal 120 over 1 plus 1. Oop, just kidding. S prime of 1 is negative 120 over 1 squared plus 1. That's going to be a negative. Okay? We know this is going to give you 0. If you had a hard time with this, please review how finding mins and maxes work. And then I'm going to choose another number to the right of 2 root 30. 2 root 30 is like uh root 120 is like around 10-ish or something like that, a little more than 10. So I'm going to choose a really big number. I'm going to choose like 100. That's going to give negative 120 over 100 squared plus 1. And that's going to give me a positive number. You don't know how that happened? Work it out. Um, and then, oh no, I circled and forgot to get rid of the t. Oh, there we go. Yeah, so positive. So this is going to go like that. It's 0 as a rate of change, and then shoot back up. That is in fact a min. So we know that, there we go. So we know that b is equal to 2 root 30. Okay? And then our final step is solve for remaining variables. Okay, we know, I'm going to use an easier equation, okay? I'm going to use this, okay? A times B is equal to 120. A times B is equal to 120. We know that B is equal to 230, which is the square root of 120, which means we have A times root 120 is equal to 120. And then you say, oh, yeah, that means A is equal to 120 over its own square root, which is equal to square root of 120. And then the final answer is going to be, I'll put it in like, I don't know, hot pink. A equals 2 root 30. B equals 2 root 30. Pop that in. Easy. This is more or less how I would organize it. I'd space it out a little bit more. Obviously, I'm writing kind of big so you guys can see, but like, yeah, it's not hard. Y'all got this. Okay. So let's do problem number 2. Okay, this one's actually very, very fun. For problem number 2, you have y is equal to square root of x. Find the point on this curve that is closest to 5 comma 0. Okay, so your initial equation, actually, I'm not going to bother with making the colors match, okay? Like, it's okay. So your initial equation is going to be initial equation, starting equation, doesn't really matter what you call it. We're saying closest, we want distance, okay? And distance is going to be, you know what, we'll get there. So you know your first equation is y is equal to root x. 2, you know your point is 5 comma 0. And 3, you know distance of point 1 and point 2 is equal to x2 minus x1 squared plus y2 minus y1 squared. You want to optimize this, right? Because you're trying to minimize. Okay, so your equation. Okay, now you want to turn all of this into a single variable situation because that's easier. Okay, you know that the distance in terms of 0.1 and 0.2 is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared, right? Okay. Let's remember, we know that 0.2, the second point, right, is going to be 5, 0. Okay. That means that you reduced it down from a 2-point situation to a 1-point situation. So that means because you already plugged it in, it's a known value, right? It's going to be x2 minus, you don't even need the 2 because there's only one x now, right? X minus 5 squared plus y minus 0 squared. Easy money. But then you'll note the curve is y equals root x, which means points on the curve are of the form x comma f of x, right? Or x comma root x, if you will, right? Because you know that's what y equals. So then you can turn this from a two vari 2.2 variable situation to a 1.2 variable situation to a one variable situation, because you can write this as x minus 5 squared plus, what does y equal? Oh yeah, root x, right? And that you can write as, distribute this out, x squared minus 10x plus 25. This is plus x. That equals x squared minus 9x plus 5, 25, which you can write for derivative purposes after as x squared minus 9x plus 25 to the 1/2. Easy money. You now have the single variable equation of the thing you're trying to optimize. At this point, I would circle it so you don't lose it. Okay? Now that you have things in a single variable form, we're gonna derive it. Okay. You have distance in terms of x is equal to x squared minus 9x plus 25 to the 1/2, which means you know your derivative. Just a quick little whatchamacallit, just a quick little chain rule is going to give you, I'll do this in, let's not do an orange, let's do it in a nicer shade of green. Derivative of the distance is going to be 1/2 x squared minus 9x plus 25, so negative 1/2 times the derivative of the inside, which is 2x minus 9, and that's kind of ugly, so you can actually write that as 2x minus 9 on top, all over 2 square root of x squared minus 9x plus 25. Okay, easy peasy, right? Okay, now after we find our derivative, we want to find our critical values, yeah? So we know d prime of x is equal to 2x minus 9 all over 2x squared, oops, actually we'll write this, x squared minus 9x plus 25. Okay, again, our critical values occur when d prime equals 0 or d prime undefined. However, we want to min. And mins only happen when d prime equals 0, not undefined. So we don't actually care when this equals 0. We care because, sure, yeah, that causes problems, but that's the interesting part, you see? Okay, so you'll have d prime equals 0 when 2x minus 9 all over da 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 equals 0. You multiply blah 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 to the side, and that gives you 2x minus 9 equals 0, which gives 2x is equal to 9, which gives x is equal to 9 halves. Also, incidentally, this will never equal 0 because the discriminant is negative, but y'all don't need to know that. Okay, once we have this, we will verify. I just used orange. Let's skip green. Okay, let's make sure we're all within our constraints. There are no constraints other than these constraints. Okay, cool. So, uh, pick a number less than 9 halves. I'm gonna pick 0. Okay, I know that d prime 0 is going to be negative over positive, which is negative. I'm going to do d prime, that's a 4 half, or 4.5. Let's do 10. It's going to be 2x minus 9. 20 minus 9 is positive. Denominator is also always positive. That's positive. So yes, this is our max. Okay. So now what we have to do is solve for remaining variables. So we know x is equal to 9 halves. We know based off of the first page that y is equal to root x, which means, plug it in, equal to root of 9 over 2, which is equal to 3 over root 2, which can also be written as 3 root 2 over 2. If you don't know how I got from here to here or here to here, check your algebra. Okay, cool. So your final answer, your point is going to be 9 halves, comma, 3 root 2 over 2. Easy money. No notes. What I'm going to do is solutions for 3 and 4 will be provided via PDF and not recorded. I'll probably post it at the end, but I won't walk you guys through it. Okay. Okay. Thank you for your attention. See you guys another time.